Last but certainly not least, 7.4. Operational properties number 2. This one's a little bit shorter than 7.3, but it's the same spirit, right? We're looking at ways to calculate complicated Laplace transforms, right? Ways to calculate complicated Laplace transforms. So, first things first, a theorem. If the Laplace transform of f is big F, then if you take the Laplace transform of t to the n times f, what you do is you take the nth derivative of the original Laplace transform, right? So f transforms into capital F. In order to calculate the Laplace transform of t to the n times f, you just take n derivatives and multiply by plus or minus 1 accordingly, times f of s. All right, so let's look at this in action. If I'm going to calculate the Laplace transform of t sine kt, well, in that case, I take the Laplace transform of sine kt, and I take one derivative, right, because n equals 1 in this case. So I take one derivative, and I raise negative 1 to the first power. Okay, we know the Laplace transform of sine kt, right? It's k over s squared plus k squared. And then all we need to do is take one derivative, ds, and multiply that by negative 1. This is a good part where it's good to remember the quotient rule. Right? Remember the quotient rule. Low d high, so derivative of k with respect to s is 0, minus high d low, derivative of s squared plus k squared ds is 2s, all over low squared. Times negative 1 out front, right? Don't forget that guy. And this goes to 0, and we get negative times a negative is a positive, 2ks over s squared plus k squared all squared. So that's the Laplace transform of t times the sine of kt. So again, anytime you multiply by t's, so if we remember pre-multiplying by e, like e to the alpha t, right, that does a shift of the Laplace transform. Multiplying by t to the n, right, like in this case, takes derivatives of the Laplace transform. So both t to the n and e to the alpha t just, right, they just shift or change the Laplace transform of the regular function, right? Sines and cosines. Okay, let's look at another example. Laplace transform of t e to the 3t. Now, there's two ways we could do this. Either we can view this as a shift of the Laplace transform of t, like I did here. So this is option 1. Right? Either this is a shift, an e to the 3t shift of t, in which case we find the Laplace transform of t and then we shift from s to s minus 3, right? Laplace transform of t is 1 over s squared, which means Laplace transform of t shifted is 1 over s minus 3 squared. That's option 1, right? Option 2 is we view this as a derivative operator on the Laplace transform of e to the 3t, right? So this is t to the first power times some function of t. So we can view this as first derivative times negative 1 of the Laplace transform of e to the 3t. And the Laplace transform of e to the 3t is 1 over s minus 3, which means taking the derivative, you get, what do you get? You get negative 1, s minus 3 to the negative 2, and you multiply by a negative 1 out front, so you get 1 over s minus 3 squared. And we can see that these are equal as they should be, because they're both equal to the Laplace transform of t e to the 3t. So this is option 2. This is option 1. So we can see that no matter what you do, you get to the same conclusion, which is what we'd hope, right? That's what we'd hope. Let's solve a differential equation, an initial value problem, right? Solve an initial value problem. Taking Laplace transforms of both sides, right? Laplace transform of x squared is this, s squared capital X of the s minus s of x naught minus x prime at 0. Laplace transform of 16x is 16 capital X. Laplace transform of cosine 4t is s over s squared plus 16. We also know that x of 0 is 0, and x prime of 0 is 1, right? So this goes to 0, this goes to 1. We're left with, we can move the 1 across the equal sign. We're left with s squared plus 16 times x 1 plus s over s squared plus 16. Excuse me. Okay. Divide both sides by s squared plus 16. 1 over s squared plus 16. S over s squared plus 16 all squared. Now, example number 1, right? If we look at example number 1, the conclusion was that the Laplace transform of t sine kt looks like this, right? It looks like number times s over s squared plus k squared all squared, right? Number times s over s squared plus k squared all squared. So if we look back down here, this is close, right? This is number times s over s squared plus 16 all squared. And 16 is 4 squared, right? So this is almost, well, I said cosine there, it should be sine. This should be sine, sorry. This is almost t sine kt, right? We're just missing a little bit right here. We're missing a 2k, right? So we're missing we need 2 times 4 on top, right? We need a 2 times 4 right here for this to be the inverse, the Laplace transform of t sine kt. So using k equals 4, right? We know that we need to add a 4 up here as well, right? And divide by 4 out front to make this a sine. A sine Laplace transform. So we get a 1/4 sine 4t. And then we need a 1 over 2 times 4 to make this a t sine t. T sine 4t, excuse me. And that's it. That's it. So overall, if you see a bunch of these, right, you kind of get the impression that maybe you don't have to always run partial fractions. And that's kind of the hope. That's kind of the hope. The next thing also helps with avoiding partial fractions sometimes. So if you've never seen this before, this is just a product of functions. It's defined in a strange way, but it is a nice product, okay? So if f and g are piecewise continuous on the positive t-axis, whatever they're defined on, the positive real numbers, then the convolution of f and g is this function, f star g, right? This is the convolution. Convolution of f and g. It's defined to be the integral from 0 to t, right? So this is a function of t, right? Function of t. This is defined as the integral from 0 to t, f, a function of x, so whatever f was before, make it a function of x. G, whatever it was before, make it a function of t minus x. T minus x. Dx. So this integral dx like removes, right? Removes all x's. So we're just left with this t, right? Some books, instead of using x, they use tau in all these spots. But I don't like that because it looks a lot like t, and that's really confusing. So I prefer to use x, but I'll use both. I'll use both. So like I said before, convolution is a generalized product, and it's a function of t at the end of it. So let's look at an example of like doing convolution. This is just find the convolution product of e to the t and sine t, right? By definition, right, f star g is integral from 0 to t, f of x, g of t minus x, right? So these are both functions of t, but now we're going to make this be a function of x and this be a function of t minus x, right? So no matter what they were before, now e convolution sine is the integral from 0 to t, e to the x, right, function of x, sine of t minus x, function of t minus x, dx, right? And now we got to calculate this, which is not too bad. It's going to be one of those double integration by parts things. Anytime you have an exponential and a trig function, you got to do double integration by parts. So we do the first integration by parts. We put the trig functions in the u column, so we're going to have to do that again later. Again, we get u times v minus v du. This is the first integration by parts, right? And now we need to run integration by parts on this chunk. So we do that again. Make sure we put the trigs in the same column, right? U times v minus v du. Now we get this, right? And if we notice, the convolution product of e and sine is this integral, right? The convolution of e and sine t is this integral, which means this integral here is also the convolution of e and sine. Also the convolution of e and sine. And we just need to evaluate these things, right? These are not hard to evaluate, though. So we can move this across the equal sign, right? Take this whole thing and move it across this equal sign and combine it with this one. So this is a minus convolution. When you move it across, it becomes a plus convolution. And when you combine it with this, you get two of those on the left-hand side, right? So two convolutions is this and this, evaluated at 0 and at t, right? Plugging in x equals t, we get e to the t sine of 0, which is 0. Plugging in x equals 0, you get e to the 0 sine t, which is negative sine t. Plugging in x equals t, you get e to the t cosine of 0, which is 1. So you get e to the t. And then plug in x equals 0, you get e to the 0 cosine t. E to the 0 cosine t. Which means, excuse me, we get 2 of these equals minus sine t plus e to the t minus cosine t, right? So dividing by 2 on both sides, we get the convolution is equal to 1/2 e to the t sine t cosine t. So this is how you calculate a convolution of e and sine. Now, not all the convolution products are this hard to calculate, and some are even harder to calculate. So you have to be careful, I guess you'd say. But anyway, that's not the big focus of this, right? The big focus of this is how does convolution behave in relation to the Laplace transform. So let's say we have the Laplace transform of e to the t sine t. Well, we just calculated it. Sorry, convolution. We just calculated what this convolution product is equal to, right? So this Laplace transform is the same as this Laplace transform because these things are equal. We can calculate this Laplace transform, right? Split this up over the subtraction and addition, right? Laplace transform of e to the t is 1 over s minus 1. Laplace transform of sine t is 1 over s squared plus 1. And Laplace transform of cosine t is s over s squared plus 1. Now if we clean this up, we can combine all these things together to be 1 over s minus 1 times s squared plus 1. And this looks like 1 over s minus 1 times 1 over s squared plus 1, which is the Laplace transform of e to the t multiplied by the Laplace transform of sine t, right? This is true in general, right? In general. The Laplace transform of f convolution g is the product of the Laplace transforms, right, as functions of s, right? These are functions of s. So as functions of s, the Laplace transform of the convolution product is the product of the Laplace transforms. That's a mouthful to say. And it's also true that f convolution g is the same as g convolution f. This is not obvious, right? Even like in this case. I can't imagine that swapping the role of these two would lead to the same conclusion, but it does. You can check. If you do sine t times e to the t minus x, you'll see that you get to the same exact convolution product, which is kind of wild. It's kind of wild. Okay, here's an example. What's the Laplace transform of integral 0 to t e to the tau sine of t minus tau d tau? Well, this looks like a convolution product, and in fact it is. It's the convolution of e and sine, right? E and sine. And we know the Laplace transform of a convolution product is the product of the transforms, and we've already calculated both of these, so we know that this is the Laplace transform of this integral, right? So this is going to be useful for solving equations whenever there's an integral equation involved. Okay, here's another example. Laplace inverse of 1 over s squared plus k squared squared. Okay, if there was an s up top, right? If there was an s up top, this would be close to t sine kt that we saw before, right? If there was an s up top, it would be that t sine kt that we've seen before. But since there's not an s up top, what can I do? Well, I can split it, right? I can split it to be 1 over one of these times 1 over one of these, right? And now this is a product of functions of s, right? And if I compensate on top to add some k's, right, these both look like sines. These are like transforms of sine functions. And by the theorem, the inverse Laplace transform of a product of functions of s is the convolution product of the functions of t. Right? So this is 1 over k squared sine kt convolute sine kt, because that's the inverse Laplace transform of each of these separately. Okay. So now we got to find the convolution product of sine kt convolute sine kt, right? By definition, this is integral 0 to t sine kx sine of k t minus x, right? And there's this convenient little product to sum formula in the trig functions, right? This is the trig product to sum. Formula. We know that sine times sine is 1/2 cosine of the difference minus cosine of the addition. So this really becomes, we gotta compensate for the 1/2, right? Sorry, the 1/2 comes out front is what I mean to say. But the sine times the sine becomes cosine of the difference plus minus cosine of the sum, right? Kx minus k times t minus x is 2kx minus kt, and kx plus k t minus x is just kt. Okay, we can integrate this, right? We can integrate this. Integrate this dx right? Integrate this dx, you get 1 over 2k. Integral of cosine is sine, keep the inside, minus integral of this dx. This is just a function, this has no x's, right? No x's. So the integral of this is like a constant dx, right? Constant. With respect to x. So the integral of this dx is just x times the cosine. And then we evaluate at x equals t and x equals 0, and we plug it in, and we simplify it down, and we get to this. So this is the inverse Laplace transform of 1 over s squared plus k squared squared. Not what we would expect. Okay, here's a little side note for you. Transforms of integrals. If you just have an integral by itself and you transform it with the Laplace transform, you can view this as the integral of f times 1, right? F times 1, which means this is the convolution product of f of t in 1, which means this is the Laplace transform of f times the Laplace transform of 1, which means this is f of s over s. And this is kind of useful. This can save us often from doing partial fractions, right? Because the inverse Laplace transform of f of s over s is just the integral of little f, which is the inverse Laplace transform of big F. Let's see this in action, right? Let's say we're taking the inverse Laplace transform of 1 over s times s squared plus 1. Normally, we'd have to split this up, right, using partial fractions. But in this case, since s is one of the factors, right, we can rewrite this as 1 over s squared plus 1 over s, right? 1 over s squared plus 1 over s. And now, this is capital F of s over s, right? Capital F of s over s. And the inverse Laplace transform of 1 over s squared plus 1 is sine t, right? Sine t. So that means this becomes the integral from 0 to t, inverse Laplace transform of this as a function of x dx. And we know that this is sine x, and the integral of sine is negative cosine. Plug in 0, plug in t, you get 1 minus cosine t. So this would have split up nicely is the point, right? This would have split up nicely. But it's okay. So there's multiple ways to skin a cat usually is the deal. Okay, here's a nice use case of Laplace transforms. Let's say we have, this is called an integral differential equation, right? An integral equation in this case. Right, it's an equation involving a function and its integral, and we're asked to solve for this function of t. Well, since this is an integral that looks like a convolution, it could be helpful to take Laplace transforms everywhere. Taking Laplace transforms of both sides, you get Laplace transform of f, Laplace transform of this creature, and then the Laplace transform of this. And we know that this, right, this is a convolution. This is f star e to the t. This is s star e to the t. So you get capital F of s. This transforms into this, and this Laplace transform is really this Laplace transform. We'll keep going, cleaning this up a little bit. This becomes Laplace transform of a convolution product is the product of the Laplace transforms, right? Laplace transform of f is capital F. Laplace transform of e to the t is 1 over s minus 1. Now we have an equation involving only capital F. So if we can solve that and untransform it, we'll have solved for little f. So we get f of s equals s minus 1 times s times all this stuff, cleaning it up, just pass this into both parts. We get 6s minus 6 over s to the 4th. Split this up, right, into two parts. We can do partial fractions on this bit. It's not too hard. F of s equals this. Now we can take inverse Laplace transforms everywhere, right? This is missing a 2 factorial on top. This is missing a 3 factorial on top, right? This isn't missing anything, and this is fine. So after untransforming it, we get f of t equals 6 over 2 factorial t squared minus 6 over 3 factorial s to the 4th, t to the t cubed. This is the Laplace transform of 1, and this is the Laplace transform of e to the minus t. So we solved that integral differential equation for little f using Laplace transforms. Okay, last. Transforms of periodic functions. Periodic functions are like wave functions, right? Think sine t, sine and cosine, and tangent, and all those other things. And there's also like square waves, right? There's like sawtooth waves, right? There's like extreme sawtooth waves, right? Things that look wave-like are periodic functions, right? And the period is how long it takes to repeat a single cycle, right? So if we look at this function down here, right? This has period 2, right? Because after 1, 2, right? After this bit, you repeat, right? And each of these has length 2. So that means period is 2. Sine and cosine have a period of 2 pi, right? Because if you think about the sine and cosine functions, right? They go up, they come down, they come back up. And, well, it takes longer than that. I guess 2 pi would be like 6, right? So they go up, they come down, and they come back up, right? And that's one cycle of a sine or cosine, which means they have period 2 pi. So these are periodic functions, right? Periodic functions have this property that f of t plus some capital T is the same as f of little t, right? And this big T right here is called the period. Okay, if you have a piecewise continuous function which is periodic with period t, then its Laplace transform can be calculated using this formula, right? Where this is the period, and this is the part that doesn't, this is the part that's defined on the first interval. Okay, that's complicated to say. Let's look at an example. So let's look at the Laplace transform of the square wave function, this guy. All right, the square wave. So the square wave has f of 1 and 0, and it has period 2, right? So from 0 to 1, it's 1, and from 1 to 2, it's 0, and then it repeats itself. That's what this means, right? F of t plus 2, this is the period, is the same as f of t. We can use this formula, right? The Laplace transform of the whole function f, which goes across the whole real line, right? It looks like this, right? The Laplace transform of that entire function is 1 over 1 minus e to the negative s times 2, right? Negative st. Integral from 0 to 2, right? Integral from 0 to period. E to the negative st, right? That's just hanging out. F of t. And this is f, right? This is f. So the integral from 0 to 2 of e to the negative st f can be split up into the integral from 0 to 1, e times f, plus the integral from 1 to 2 e times f. This is hanging out, right? The integral of this is dt is negative 1 over s e to the negative st from 0 to t, so from 0 to 1. This is 0, right? This is hanging out still. And after you calculate this out, you get 1 minus e to the negative s over s times 1 minus e to the negative 2s. This is the Laplace transform of the square wave function, right? Square wave transforms into this. That's it. That's the end of the material. So this is the end of test 3 material and also the end of the final material. Thanks for tuning in, and good luck to you on your tests.